Hi, I'm Raluca Rufu from Southwest Research Institute as well. So Brenna talked to us about forming the moon after a canonical giant impact. And these impacts typically leave the system with the Earth-Moon system with an angular momentum that is consistent with the current value. However, is it better? Okay. Hopefully you got some of that. Okay, so there's a suite of proposed impact scenarios that assume a higher angular momentum, and these are beneficial because they create more mixing between the debris disk and the protoplanet. And therefore, it creates a debris disk that is more Earth-like and would create a moon that is Earth-like and explain the isotopic similarities without needing any post-impact equilibration. However, for these impacts to be viable for the Earth-Moon system, you need to remove the angular momentum that is sometimes twice or even more the current value. So some mechanisms were proposed. One of these is the evection resonance. And the second is if you have a high obliquity Earth, you can maybe do this with the Laplace plane instability. And I'm going to focus only on the evection resonance in this presentation. This is because this resonance is the first one that is encountered, and the Laplace plane instability will be encountered when the moon is farther away from Earth. Okay, so what is the evection resonance? This is a resonance between the Earth, moon, and the sun, and it occurs when the precession period of the moon is exactly 1 year. So initially, after the formation, the moon is going to tidally evolve outward on a circular orbit, and it's going to conserve angular momentum. The spin of the planet is going to decrease, and the orbit semi-major axis of the moon is going to increase. Eventually, the moon is going to reach where the precession period is exactly 1 year. And in that case, it's going to see the sun at exactly the same angle at perigee. And there's going to be an excess net solar torque, and is going to increase the eccentricity. So now what controls the eccentricity instead of the tides is the sun. So therefore, the angular momentum is no longer conserved, and angular momentum from the Earth-Moon system is transferred to the Earth-Sun system. And as you can see that initially the moon librates around this 90 degrees between the Earth, moon, and the sun, but eventually these librations grow, and it's going to enter a regime which we call the quasi-resonance, where the eccentricity is still being controlled by the sun, and the angular momentum is still being removed from the system, but the precession period oscillates around a value that is smaller than 1 year. The semi-major axis now decreases, eccentricity decreases, and the moon is going to pass evection, this dashed line, one more time, and its further evolution is going to occur with constant angular momentum. So you can see that in this example, we started with an angular momentum that is more than twice the current value, and at the end, with evection, we were able to successfully remove enough angular momentum to be consistent with the current value. So we have done these kind of simulations for a wide range of tidal parameters. And what we concluded from these suite of simulations is that if the moon migrates very fast, so this Q over K2, which I'm going to talk a lot about, so this Q over K2 is low, the moon is going to pass evection too fast to get captured, and therefore the angular momentum will remain large. So these are all these red bullets. And the opposite is true if there is a slow migration. So these are if Q over K2s are very large. So for slow migration, this quasi-resonance is going to maintain until the co-synchronous state is reached. So when this is the Pluto and Charon case. So we know this is not true for our Earth-Moon system. And in between, you have a range of successful cases where you are able to get captured into evection resonance and then exit the quasi-resonance to be consistent with the current value. And what we concluded is that in a narrow range of successful cases, indeed, our evection resonance is efficient in removing enough angular momentum. But now we have new evidence that suggests that this simplistic model that we have created over here that I'm proudly showing you may not be realistic for the Earth-Moon system. So for one, we assumed that the tidal parameters in these simulations are constant. And we think that this might not be true because after a giant impact, the Earth's mantle is fully molten. It has a very low viscosity, and therefore initially it doesn't have enough power to push the moon outward. So at first, the tidal migration is very slow. But eventually the Earth's mantle is going to start to solidify and the viscosity is going to increase, and therefore the moon is going to migrate faster and faster. But beyond the dependence of the viscosity on the temperature of the Earth, there's also dependence on the Earth's rotation. So here in this figure, you can see the semi-major axis over the Earth's rotation. And the colors is all the Q over K2, so how fast the moon migrates outward. And you can see that for low rotations, we have regions of Q over K2s that are large. So we think that evection resonance can indeed occur in these regions. However, for fast rotations, these are the cases for high angular momentum impacts, the dynamical tides dominate as opposed to the equilibrium tides, which are usually assumed for the Earth-Moon system. And these dynamical tides cause resonances inside the magma ocean to get excited, and therefore Q over K2 is going to plummet or even reverse its direction. So everything beyond 1.8 LEM, we think that it could not get captured into evection resonance. And this is in contrast with what we get from impact simulations that suggest 2 or more LEM. And as the Earth cools, the tidal migration becomes faster, so you see all these bluer regions. So really, in order to understand whether evection resonance is efficient in order to remove angular momentum from the Earth-Moon system, you really need to do the thermal evolution of the Earth together with these dynamical tides, and also do the thermal evolution of the Moon. And these two processes are going to have to occur concurrently because they rely on each other. So that is exactly what we did in this study. And in this model, the Earth's cooling rate is a function of how much heating is introduced to the tides and how fast the Earth is able to radiate its heat through its atmosphere. And we assume a CO and H2O rich atmosphere. We assume different types of atmospheres with different varied water content. And what we find is that for atmospheres that allow for fast cooling rate, these are the non-gray atmospheres, the Earth is going to cool too fast and the Q over K2 is going to be too low to allow for the moon to get captured into evection. So angular momentum is just constant. For slower cooling rates, and these are enabled with a gray atmosphere, which you would argue that this is the less realistic case, and I would agree with you. We get captured into evection, but eventually the Earth is going to cool down. The K over K2 is going to be too low, and quasi-resonance, we're going to skip from quasi-resonance. So even if angular momentum is somewhat removed, it's very limited. And we have done this for different amounts of initial angular momentums. And consistently, we see that even if you get captured into evection, the angular momentum that you get, that you removed, is limited. So to conclude, we modeled for the first time the thermal evolution of the Earth and included dynamical tides. And together with the lunar tidal evolution through evection resonance, we found that these dynamical tides suggest that rapid lunar tidal migration for fast spinning Earths, and these are exactly the rotations that are suggested from impact simulations. And we saw that there is a very limited angular momentum that could be removed in these cases. So what we are going to argue is that either we need a different mechanism or that high angular momentum impacts are not viable scenarios. Thank you.